Hey everyone, the last time I already teased that to understand logic gates, we have to understand transistors. Because logic gates are pretty much just transistors combined together in a specific way, depending on the particular logic gate. But we will get to that in the next video. In this video, we will take a look at what a transistor does and how it works. And I do like this music, I gotta be honest. A transistor is a semiconductor, which simply means it is not an insulator like glass, but it also not really a conductor like copper. And that is precisely why semiconductors are so useful. They only conduct in certain circumstances that we can manipulate. In case of the transistor, it only conducts if a third wire, the base, is connected to the positive terminal of a battery. Probably the simplest semiconductor is a diode. It only conducts electrons in one direction, at least up to a relatively high threshold. This works because of the material that a semiconductor is made of. You probably already guessed it, we are talking about silicon. But the funny thing is, silicon in its pure form is in fact an insulator, meaning it doesn't conduct electrons at all. After all, silicon is what glass is made of, together with a couple of carbon and oxygen atoms and stuff like that. But if we mix it up with some phosphorus or boron, it starts to conduct a bit. These mixtures are called doped silicon, and we use either phosphorus or boron. When we dope silicon with phosphorus, the silicon crystal has a slight surplus of valence electrons that can engage in a covalent bond. Therefore, they are free to move around in the silicon crystal. On the other hand, if we dope silicon with boron, the crystal has a slight shortage. Now, if you hook up a phosphorus-doped or N-type silicon crystal to a battery, the surplus electrons flow to the positive terminal of the battery, leaving behind holes in the N-type crystal. Electrons from the negative terminal of the battery then can take up these holes, and the N-type crystal has a surplus of electrons again, and the process repeats. In simple words, that means it conducts. Now, a boron-doped or P-type crystal does pretty much the same, only that it starts with having holes where electrons from the battery can move to, and then exit the crystal and flow back to the positive terminal of the battery. Watch what happens if we combine an N-type crystal with a P-type crystal. The electrons in the middle fill up some of the holes of the P-type crystal. This leaves the middle relatively stable. When we connect the N-type side of the negative terminal, it gets even more electrons. Some of them get close to the P-type crystal and then populate the P-type crystal and exit the semiconductor on the other side. But when we connect the semiconductor the other way around, the positive terminal attracts electrons from the N-type crystal, reducing the surplus, and the negative terminal provides electrons to the P-type crystal, reducing the number of holes. This leads to an expansion of the depletion area in the middle, and none of the remaining electrons in the N-type crystal can jump over to the P-type crystal and continue to flow to the positive terminal. The semiconductor has become an insulator. So how does this help us with understanding transistors? Well, transistors also use these N and P-type materials. But instead of only one N-type side and one P-type side like in a diode, the common NPN transistor uses, as the name gives away, a N-P-N combination. If you now say, but that means that current can flow in neither direction, then you are absolutely right. But if you recall, a transistor has 3 wires. And that's actually what throws most people off when they think about a transistor. How can a component have 3 connectors if a battery only has 2? Like, we have plus and minus, so what's up with the third one? And the answer is actually pretty simple. It just connects to the positive terminal as well. That's it. Mystery solved. Well, not entirely. If we connect the input or emitter to the negative terminal and the output or collector to the positive terminal, the transistor does not conduct any electricity because the depletion area in the middle is simply too large for electrons to jump over from atom to atom. The third wire actually connects to the middle part of the transistor and is called the base. If we now hook up the base to the positive terminal of the battery, electrons do not have to jump all the way to the collector, but only to the base and can escape the transistor this way. But now that they can get further into the middle, the distance to the collector shrinks and electrons can now also reach the collector. It's like allowing a small current through the dam of a river that only seconds later breaks down the entire dam through momentum. As we usually only allow a small current to flow through the base by adding a resistor afterwards, the p-type crystal in the middle only lets a few electrons escape. The majority therefore escapes through the collector, whose naming now makes totally sense. The ratio for most NPN transistors is typically 1 to 100, meaning a current flowing through the base of 1 allows a current to flow through the collector of 100, which is why you often hear that a transistor multiplies the current. And that is pretty much it. Now, you might be confused by one thing. I thought electricity flows from plus to minus. And the answer is, well, you have been taught a lie. When Benjamin Franklin first discovered electricity in the 1800s, which he actually didn't, but that is a story for a different time, he didn't know about electrons, so he had a 50-50 chance of getting it right. And he got it wrong. It wasn't after almost 2 centuries later that scientists discovered electrons and realized, oh shoot, we were wrong the whole time. But by then, engineers had so gotten used to drawing electricity flowing from plus to minus that it was hard to get the word out. And as we know, humans are lazy creatures. And after all, we would have to flip all the circuit symbols to make sense of them. A diode has a symbol with an arrow pointing from plus to minus. A transistor has a symbol where the arrow points at the emitter. But the truth is, electrons flow from negative to positive. One thing that might help for the diode is to imagine that if the current flows in the direction of the arrow, the plate blocks the electrons. And the arrow in an NPN transistor indicates the emitter. So let's see how a transistor integrates into an electric circuit. Think about a transistor as an electrically operated switch. Here we have a simple electric circuit, a battery with 5 volts, a resistor, and an LED. Let's add a regular switch. If we close the switch, electrons can flow and the LED turns on. We use the electron flow way to show how electrons actually move through the wires. If we replace the switch with the transistor, we need to somehow hook up the third wire, the so-called base, to the positive part of the terminal. We can either hardwire it, which will leave the transistor on constantly, or we can add a switch that allows the current to flow through the base. In reality, this would be a microchip, for example, controlling the flow through the base, because otherwise it wouldn't make a difference to just using a switch after the LED. But as the current through the base is relatively low, we can use a control current to control different transistors with a microchip and not control an LED, but actually the inputs of a 6502 microchip, for example. Now, if we close the switch, the LED lights up. But this is only one condition that has to be true to light up the LED. The goal is to light up the LED based on 2 control currents. In the next video, we will finally take a look at the simplest of all logic gates, the AND gate. If you still feel a little bit unsure about transistors, we will also take a look at some more examples, as an AND gate is, spoiler, simply 2 transistors combined together. But if you want to learn more about semiconductors before, check out this video made by Khan Academy about semiconductors. They go a bit more into detail when it comes to what is happening on the atomic level in doped silicon crystals. And again, you can also check out Ben Eater's video about semiconductors, who happens also to be in the video of Khan Academy, as he is a former educator there. Otherwise, I will see you in the next video.